Hi everyone. So today we will discuss this position vector. So before we start this position vector, let us recall these unit vectors. So as we had discussed in the previous classes, unit vectors are those vectors whose magnitude is equal to 1. So magnitude of any vector, if it is 1, so those vectors are termed as unit vectors. And we know that unit vectors, they are just having magnitude 1, so they will have the same direction as the any other vector, but the magnitude of that it is equal to 1. Suppose if you consider 5 meter east, so if we consider this 5 meter east, so this is a vector having its direction towards east and magnitude at 5. Now if we want to consider it as a unit vector, then we will take it as 1 meter east. So that magnitude of this corresponding vector, as far as its unit vector is concerned, it becomes 1 meter. The simple logic is how to calculate this. So divide any vector by its magnitude, that will give you the unit vector. So 5 meter divided by 5, that is magnitude of that, and we get this as unit vector, that is 1 meter east. Now corresponding to this, we have a concept like in the coordinate system, we represent this as x-axis, y-axis, as well as z-axis. If you consider the 3 dimensions, so this is the coordinate system. We represent different points. We take the coordinate of that. Either it is 2-dimensional, we take x and y-axis. We take 3-dimensional, we take consider x, y, as well as z-axis. Significance of these axes are what? It is just mutually perpendicular to each other. So any lines which are mutually perpendicular to each other, that can be represented as coordinates or the axis. So we have x-axis, y-axis, and z-axis. Now the same thing, it can be represented in the vector form. As far as the vector geometry, you can say, is concerned, or application of the vectors are concerned. So x-axis and y-axis and z-axis, they are renamed as far as the vector representations are concerned with the help of unit vector I, j, as well as k. Unit vector I, j, and k. As far as the unit vectors I, j, and k are concerned, they are not having any dimension, they are not having any unit. It is just that x-axis is assumed to be represented by unit vector I. Once this coordinate system is considered in the vector form, this y-axis is just represented by j, z-axis is just represented by k. It means I, j, and k, they are also perpendicular to each other, mutually perpendicular to each other, as well as their magnitude, it is 1. They are not having any dimension, they are not having any unit. As far as representation of the unit vector is concerned, we always have represented with the hat or this cap. So similarly, I, j, and k we are taking at the unit vector, so they will also be represented as I cap, j cap, or k cap. So this is the significance of this. So here if you consider, this is your x-axis, y-axis, and z-axis. So we have taken this representation along unit vector I, okay, this representation along unit vector j, and this representation along unit vector k. Now why we take this as unit vector? Because if you say, suppose 2 meter east, so 2 meter, either you completely give this statement 2 meter east, or east is towards what? Positive x-axis. So if we consider east along the positive x-axis, and positive x-axis in the vector form is represented by the unit vector I. So instead of writing this entire thing, we can write it as 2i. So once you write 2i, it is understood that 2 is the magnitude of this corresponding vector, and its direction is such that it is along the unit vector I. And we know unit vector I, it is along what? Along the positive x-axis, and positive x-axis represents the east direction. So this clarifies everything. So instead of writing this, we can simply write this. If you say 5 meter north, 5 meter north means this side. So that can be represented as 5j. Okay, because we are taking this j along this. Now when we write this j here, and its magnitude is 1, so it is not disturbing, or it is not changing the magnitude of this overall vector. And that's why we consider this I, j, and k with the magnitude 1, and they are represented, they are termed as unit vectors along x-axis, y-axis, as well as z-axis. That is the only significance as far as the unit vectors I, j, and k are concerned. Now, with the help of these unit vectors I, j, and k in the vector form, we can have this concept of the position vector. And we can represent the position of any point in the coordinate system or in the vector plane with the help of I, j, and k. So that you can see. Now, suppose you have a point, let us say this point P. Okay. Now, magnitude of this point is A at an angle of this theta. It means this is represented as this vector A. We have this vector A, its location goes from this point O to B. When we say location goes from point O to this B, its magnitude of this A is OP. OP makes angle theta with the x-axis. So this component, if you consider this component, that will be how much? A cos theta, and this component will be how much? A sin theta. That we have already discussed as far as the resolution of the vector is concerned, or the finding components of the vector is concerned. So because once you drop perpendicular from here, this becomes your right angle triangle. Again, using the concept of cos theta, sin theta, you can calculate value of this as well as value of this. So this will be A cos theta, this will be A sin theta. Let us name it as AX and this as AY. Such that the resultant of AX and AY, that gives you the magnitude of this vector A, which will be AX square plus AY square root, and so on. So component of this A, along this it is taken as AX, along this it is taken as AY. Now I am using the word or a statement along this. Now instead of using this along this or along x-axis, I can simply write it as AXI. Once I write AXI, it is already understood that it is along x-axis. AYJ, so it means its component is along y-axis. So that we can consider. So this vector A, in its vector form, can you write AXI plus AYJ? Similarly, B, if there is another vector B, that will be, and its coordinate is, suppose, its coordinate is, let us say, B, so it will be BXI plus BYJ. So that way we can, if we have, suppose, vector B, like this, so it will be, its component along this will be what? BX, and component along this will be by, so this will be termed as your bxi, and this will be termed as bx byj. So that way we can represent any vector. So if in case of two dimension, if we have the vector suppose having components along x-axis, y-axis, or the vector is inclined at some angle theta, so obviously we will have some components along x and y-axis. Accordingly, those components, let us name it as ax and ay, or bx and by, cx and cy, and so on. So that can be represented like this. Once you have represented like this or this, now you don't have to say ax is along x-axis, along this direction, along this or that. This I gives us all information that this is the magnitude of the vector along x-axis. This is the magnitude of the vector along y-axis. Similarly from this. So that way we represent. So this is called position of the point A, or position. Here we have assumed this point A. Position of the point P with respect to O. Position of the point P with respect to O. Similarly, position of the point Q with respect to it. There is suppose some different point in the xy plane or this coordinate system or this vector plane. I hope this is clear. Now, see this. Now if it is suppose 3 dimension. So if it is 3 dimensions, so let us consider this x-axis, y-axis, as well as z-axis. Now along this x and y as well as z-axis, obviously we have this unit vector I, unit vector j, and unit vector k. There is a point P whose coordinate is ABC. So that I hope you understand. When we say coordinate P in the 3-dimension ABC, it means its coordinate along x-axis is A, along y-axis B, along z-axis it is C. So this can simply be represented as AI plus Bj plus Ck, because A is its coordinate along x-axis. So instead of writing along x-axis, we can say it is just AI. Along y-axis, its magnitude is B, so it is Bj. Along z-axis, it is C, so it is Ck. So OP is the position vector, position of point P with respect to O, position of this point P with respect to O. So this is your OP vector, this OP. This is clear? And that becomes your AI plus Bj plus Ck. So we term this as position vector or position of the point P with respect to the initial point, and that is also vector OP. P with this, when we say OP, so we are moving from O towards P, because once it is a vector quantity, you have to be always particular about your direction from point O towards P. So OP. If it is PO, then it will be from P towards O. So the direction will completely change. So OP it is AI plus Bj plus this Ck. Now as far as the magnitude of this OP is, because it is 3-dimensional, in 2-dimensional we have simply seen that it is just a square plus b square square root, where a and b are mutually perpendicular to each other. Here also all the 3 lines are mutually perpendicular to each other. So we get the magnitude of this OP, even if it is 3-dimensional case, it is square root of a square plus b square c square. Yani coefficient of I, j and k. Square of them, add them, square root of that. So this is the magnitude of the position vector, this P with respect to O. So this represents your position and this represents your magnitude. Now as far as the direction cosines, because it is 3, if it is suppose 2-dimensional, we simply say that this vector, if it is let us say POP, so this vector makes angle theta with the x-axis. If it is just 2-dimensional, and that is sufficient enough to locate this point P. Draw a line at an angle of theta at a corresponding distance, whatever is given, and we will get this point P, and then we can join this so that we get this straight line. So that is simple as far as 2-dimension is concerned. And we calculate, and if direction is not given, if the coordinate of point P is given, then we can, vice versa, we can calculate the direction of this OP. If it is suppose theta, then tan theta, it will be y upon x. If xy is the coordinate of this point, y upon this x. So it is very simple to calculate tan theta is equal to y upon x, because here there are only 2 dimensions, x as well as y. But if it is a case of 3 dimension, then this will, we can't say, if this makes angle alpha with the x-axis, then it will make angle 90 minus alpha with the y-axis. That we can't say, because here it is three mutually perpendicular lines. So we have to separate the direction. What is the angle that it makes with the x-axis? What is the angle this point makes with the y-axis? What is the angle that it makes with the z-axis, and so on. So let us assume that this vector OP makes angle alpha, beta and gamma. Suppose this OP makes angle alpha with the x-axis, OP makes angle beta with the y-axis, OP makes angle gamma with the z-axis. This is correct, gamma with the z-axis, like this. In that case, what will be the values of alpha, beta and gamma? So directly we can't use this relation to calculate that. Okay, so we use the cosine formula to calculate all this. So our assumption is what? This vector OP is making angle alpha with the x-axis, beta with the y-axis and gamma with the z-axis. Then to calculate alpha, beta and gamma, we consider the cosine of that such that cos alpha, it will be a upon square root of a square plus b square plus c square. What is this a? A is the coefficient here of I. When we are calculating with respect to x-axis, we consider the coefficient of this I. So coefficient of I is a, divided by the magnitude of this vector OP. So magnitude of this vector. So a upon square root of a square plus b square plus c square. When you calculate this beta, beta is the angle that it makes with the y-axis. So we will consider the coefficient of this j. So j means y-axis. So that becomes your b divided by square root of, again same as mod of OP. Gamma is the angle that it makes with the z-axis, so that we get cos gamma is equal to c upon square root of a square plus b square plus c square. So in short form you can write cos alpha is equal to a upon mod of OP, cos b cos beta is equal to B upon mod of OP, and cos gamma is equal to C upon mod of this. So that way we can consider. A, B, and C are the corresponding coefficient along x-axis, y-axis, as well as z-axis. So this way we calculate the direction cosines that vector makes with the x-axis, y-axis, as well as z-axis. From here, if you want to calculate alpha, beta, and gamma, then alpha will be cos inverse this, beta will be cos inverse this, gamma will be cos inverse this. Using this relation, you can particularly get the value of alpha, beta, and gamma. Now, if you observe these three equations, so denominator is same. So square all this. So cos square alpha, it will be a square upon this. Cos square beta is b square upon this. Means square root will be over. That is not there. Cos square gamma c square upon this. If you add them, so in the numerator you will get a square plus b square plus c square, because denominator is same in all these three cases. They will get cancelled, so we will get 1. So it is taken as a standard relation. It's very simple, but sometimes it is used to simplify problem. So we have that sum of the squares of the direction cosine, it is equal to 1. So cos square alpha plus cos square beta plus cos square gamma, that is equal to 1. So we have this feature, you can say, you can keep in mind, or you can just analyze from here. Now let us see how to use the position vectors to calculate the position of one point with respect to another. When we say this OP, okay, so coordinate of this P is not, O is the origin, so coordinate of origin is always 0, 0, 0. So if it is suppose A, B, C, so simply we write AI plus BJ plus CK and so on. But if we have different points, let us say we have this point P, and its coordinates are A1, B1, C1. There is another point C, its coordinates are A2, B2, C2. Then what will be the coordinate of P with respect to Q? Or what will be the displacement from P to Q, or displacement from Q to P? When we say position vector OP, so this is the displacement of point P with respect to, this is the displacement of point Q with respect to. What is the displacement from this point to this point, or from this point to this point? How to calculate that? So let us just see. So P coordinates A1, B1, C1, so we know OP, A1I, B1J plus C1K. Similarly, Q coordinates A2, B2, C2, so we have OQ, A2I plus B2J plus C2K. Now PQ, when we say this PQ, so PQ means what? Q minus this P, means OQ minus OP, that becomes your PQ, right? That you can get from the vector addition. If you consider this line, OP, can you say OP plus this PQ, that is equal to your OQ. OP plus this PQ, that is equal to OQ. Because if you recall again the conditions for the vector addition, head of one vector has to be joined with the tail of another vector, then join the tail of the first with the head of second, that gives the resultant of the vector. So here we have OP, here it is the head. PQ, here this is the tail. So this plus this makes it this. So you have this relation. Our requirement is what? PQ. So calculate PQ from here. That is OQ minus OP. So PQ is equal to OQ minus OP. O is the origin, having always coordinate 0, 0, 0. As far as the calculation part is concerned, it doesn't make any impact. As far as subtraction or addition is concerned, because 0 it is added, subtracted, it hardly makes any difference. So always, instead of saying OQ minus OP, using this nomenclature, we can just have short form of this, and we can ignore always speaking or pronouncing this O. So we can just write Q minus this P. This is just for our convenient, otherwise you can always use it. So Q minus P. So that's why I said PQ, the right side term minus the left side term. Q minus P, because when you calculate PQ, always you don't have to do all these things. Someone says calculate QP. Now we will not go for all these. These are some understandings. Okay. So now if you want to calculate QP, means the right side term minus the left side. It means here it will be PQ. Here it is what? PQ means Q minus P. If it is QP means it will be P minus Q. And that again we will calculate from here, this way. So we can ignore all these terms once we have understood it. Now let us apply. As far as application is concerned, we need to save some time. So that's why we will consider. So right side term minus this left side term. So PQ, that becomes Q minus P. Q means what? OQ. When we say Q means it is understood, it is OQ. When we say P means it is OP. So Q minus P means this minus this. So I is added and subtracted with I, J with J, and K with K. So when we subtract it, so A2 minus A1, we have this, B2 minus B1, C2 minus this C1. So we get this one. So A2 minus A1I plus B2 minus B1J plus C2 minus C1K and so on. So that way it gives you position of one point with respect to the another point in the complete vector plane or the coordinate plane. So that way we can calculate position of one point with respect to another point, and this gives you the displacement. If you want to calculate the magnitude of this displacement, how much it has moved from this point to this point or vice versa. So again, magnitude, you know this, square root of this square plus this square plus this square. So that way you can calculate. Again, if you want to calculate the direction of this, again you have to consider the direction cosine. And cos alpha, cos beta, cos gamma. That means it makes angle alpha with the x-axis, so we can calculate cos alpha. If it makes angle beta with the y-axis, we can calculate cos beta. And similarly, if it makes angle gamma with the z-axis, then cos gamma. And that we have learned how to calculate all these things. So let's using this. We can calculate the magnitude, we can calculate the direction cosines, we can calculate position of one vector with respect to the another vector, or position of one point with respect to another point, which gives you the displacement of one point with respect to another point. So we have discussed almost the entire concept. We have this vector as well as this scalar. So we will be solving problems based on all these concepts. Thank you.